Hello? Okay. Well, my name is Fernando. My colleagues Alejandro and Sergi are supporting me from back there. I will do the talking. We come from the IRI, Industrial Institute of Robotics from Barcelona. It's a joint research center from the Polytechnical University of Catalonia, UPC, and the SSIC, the Superior Research Council of Spain. I will present you the platforms that we offer for TERRINet. We will group all our robotic platforms in one main talk because they share the software, and then we have two facilities we also offer. So for our robotic platforms, these are the ones that we offer on TERRINet. We have some more, but these are the ones that we have prepared. And they're called these names: Tibidabo, Anna and Elena, Theo, and Iricar. And about their hardware, this is what they have. Tibidabo are two platforms meant to work in urban environments, doing navigation among people and with people, and interacting with people. To do so, they have a Segway platform and caster wheels, because when it's not in balancing mode, we use the tractor mode and we have these caster wheels. We have 2D horizontal front and rear lasers to do navigation, obstacle detection, and also people detection at that level. And for the interaction with people part, we have 2 degrees of freedom arms to just do gestures, 3 degrees of freedom neck, and some LED face expressions. And also a stereo camera on the eyes. We also have a speaker, touch screen, an emergency button, because all these are prototypes we built for some research projects, so we always need the emergency stop button, a router, onboard computers, and a router for the network, and we access through Wi-Fi with a laptop. Well, and that's it. Then we have Anna and Elena robots, which are based on a Pioneer 380 and Pioneer 280 platforms, skid steering platforms. And for these ones, we have added, the platforms are old, but we have renewed them with new computers and new sensors. And we have a stereo camera, the RealSense D435 for navigation, and also a 3D leader, Velodyne or RoboSense, one for each, to do this 3D navigation. The TV and Davo platforms only had the 2D information, and with these ones, we want to achieve this 3D or 2.5D, because we project the 3D information into 2D maps and cost maps. Touch screen, then a pan and tilt camera. This is a set stereo camera to do this final end user interaction, because these robots are meant to do tasks like package delivery, last mile package delivery, and so on. Then we have Theo, which is based on a Segway RMP 400 platform, and it has also horizontal 2D leaders and a 3D leader, which is actually a 2D leader spinning, and GPS, IMU, safety bumpers. This is meant to work in outdoor environments to do 3D mapping and also simultaneous localization and mapping. And finally, we have the Iricar, which is based on a golf car. It has a Velodyne 32 beams on top, a Ladybug 2 camera, 360 degrees field of view, also an horizontal leader and safety leaders. And the main thing here was the platform is an Ackerman with throttle and steering, and that was a challenge to do the navigation with an Ackerman platform. Okay, all these platforms, we work with the same environment. We use Ubuntu Linux, we are on 16.04, and ROS on Kinetic. We may move to 18.04 and Melodic, but not yet, we are not yet ready. And we use for simulation Gazebo, the Gazebo coming with ROS. We have all our code in a local GitLab server we have, or moving most of it there, and almost everything we have is or will be open source. We try to have all our code documented with Oxygen, and when for some custom libraries we do technical reports to summarize all the effort done and to be able to explain it to future users. And for the platforms you saw, we are starting to finish the tutorials and procedures to use them. They need to be useful for us, for our users, already users, students in our lab, and also for the TERRINet applicants that will come. And we also have experience and we use other standard libraries like PCL, OpenCV, and TensorFlow in our lab. And with experience of working with the students for some years, we have some custom tools we offer or we use at the laboratory that I will explain later. So all of these robots, they use different sensors. Some of the sensors are present on multiple of them, multiple robots. And we try to standardize the way we work with these sensors. So all the drivers of the platform, sensors and devices, we try to have an URDF of them, all the configuration files, example launch files, all following the same structure, so they are easy to use. And if the manufacturer or our provider doesn't give a ROS driver or simulation model, we build it. Otherwise, we use the one coming. And for the robot, joining all these drivers, sensors, and devices that it uses, we also have the URDF model and a complete simulation model of the robot. The robots have some basic behaviors like 2D and 2.5D navigation based on the ROS navigation stack. Also some human-robot interaction behaviors like sequences or movements of the moving parts, and some more complex tasks, but also easy combining the previous ones like guiding and following people, etc. All these developed for the research project that the robots were involved in. And also we have some custom libraries done at our labs, like a simple laser people detection and tracking. So on that image there, which tracks the IDs. It's a simple information, but is fast enough and allows us to do easy tasks involving particular people. We also developed an Ackermann local planner plugin of the navigation stack using a global planner based on SBPL and this Ackermann plugin. And you saw there our ear car following this maneuver to change the orientation, and the local planner would follow this first maneuver here. We did a technical report on that topic. And also there is a team at IRI working in this library of state estimation, basically SLAM, or we call SLAM, Simultaneous Localization and Mapping, which is called Wolf, and I think it will be released soon. I think it's not released yet, but it will be released soon and open source, and we will use it in our platforms. What else? We have tutorials for simulation and real robot that are meant to be used by the students before they, on simulation before they get to the real robot, and on the real robot when they cannot have us always doing everything for them, and procedures to handle the real robot, talking about safety and also all the procedures, the buttons you have to press, the things that should happen and not happen. These are useful for us also, but the idea is that people could use them without being us behind them all the time. But also we always give support. And constraints of these platforms is the weather conditions, because they are meant to work in outdoor environments, but as they are prototypes, we didn't solve the rain issue. So if it's rainy, they cannot go outdoors. Also the availability of a local engineer, because we need to give them support in case they need it. And maybe if the same robot is used by several people, they have to schedule for all the experiments coming. So these tools we use at IRI after the experience working with the students. One is this recommended structure of IRI ROS, what we call IRI ROS. It's based on the idea of leaving on one side the functionality. People come and they have an idea, they maybe program it on MATLAB. They should finally create a library, a shared library. And we have a ROS node structure which access one thread to this functionality to the library, and on the other part, all the ROS communication is done. So they shared these two threads, they shared data, they also have a dynamic configure server, they publish diagnostics, and we follow this structure, so it's easy for us to build new nodes and to also give support to people developing at our lab. It's easy to give support if they follow a common structure. And we also have some scripts to create these nodes automatically with just one line command. You create all the structure, and also to add topic publisher subscribers, service client servers, action client servers, and TF listener broadcasters. We actually use them. You just run the script and you have the code, all the code made, and you don't have to type all the lines. Another tool we develop and use are the ROS, what we call ROS modules, which encapsulate this client side of both actions or service, the client part, and provide an API for higher hierarchical behaviors. Um, we found using ROS and in our applications that for every time we used, we had to interface with an action or service server, we had to type all the callbacks, all the message handling, control variables to follow the flow, and define the threads. And if for our application we had to define this. So we made this shared library defining all this and simplify the use with an API, which are just, well, this is written in C++, so are just the call of to some C++ functions. We also provide some features to avoid getting stuck, because when we had some multi-robot systems, we have unreliable communications, and we had to add these timeouts and watchdogs on the actions to follow the flow and don't get stuck and be lost. Also, we have a way of accessing the dynamically configured parameters and modify them through code, because otherwise, for example, on navigation, we couldn't change the maximum velocity parameter from code, and with this, we could. And all this is based on template classes and is easy to develop, reuse, maintain, give support, and work with it. And another thing are when, well, the module thing stuff is to program these behaviors, for example, to control the navigation. But then when we want to do more behaviors and tasks, complex tasks involving several of those, we have been using behavior trees. We use this library here, which, well, is well documented there, and there are these nodes, decorator nodes, control nodes. You have to define your actions and conditions. And we add a BT layer over our modules. So the ROS node we only have to define this action and conditions depending on the application. And on the ROS node, we just need to define the XML file with the tree and use it. You need, okay, what else here? Okay, so the skills to use all these are basically Linux and GitLab version control, okay? And then to create new tasks, depend if it involves behavior trees, you need to know how behavior trees work, and mainly ROS and C, C++ or Python languages. And for the module part, just the C++ and ROS knowledge. It depends on the application, the skills needed are more advanced or less. And for the training resources, as I said, we try to document and have examples in our code. And on GitLab, on each module and each node, we have the README files. And when, as I said, for example, for the Ackermann planner, we have a technical report explaining in more detail what it is about. So this was about our robotic platforms, the hardware and software. And then we have these two facilities. OptiTrack, as someone said, you already know about it. We have at our lab now this 7x7 and 3/8 space, and we have already the cameras and have to clear out that space to increase it to double size. Here we used to do drone flights with small drones, but also mobile robots detection. When doing a SLAM, the ground truth of the OptiTrack was useful to compare with the position calculated by the SLAM software, etc. We use this Motif software on Windows and connected on network with this ROS node. And to use it, a bit of Linux and ROS to use that last part, and manufacturer documentation to calibrate, define the rigid bodies, and use it with ROS. Constraints the availability of the space because it's shared with other robots and people working there. And at last, we have this outdoor area called Barcelona Robot Lab, which is an outdoor pedestrian area of these dimensions, and it's on the university campus. So there are classrooms and students working around here, and we are allowed to do experiments there. It has buildings, open and covered areas, ramps, stairs, vegetation. We have cameras around that can be accessed by IP, and we used to use here 3G for multi-robot communication because Wi-Fi sometimes was not reliable, and it also has GPS coverage. And these are some pictures of the space from Google Maps and the photo, and this is a gazebo wall that we use for simulation. And that's it. these are all our platforms offered at TERRINet.